All right, students, good evening. I think I'll start if if there are any more to join, let them join when I talk, right? It's all quite all right. And you can ask me questions also. I hope that you can see the screen. Can you see the screen, Rishanti? I can see you there.
Yeah, ma'am, can see.
Okay, okay. And I can't remember the other person's name actually, the representative. I can remember you, Rishanti, and other one. Anyway,
Devanban.
yeah, okay. But whoever, I hope that you all can communicate whatever I say here. Uh, and also, you will have to pardon me for not putting the video because my computer is computer is a very old one and it's giving me trouble. So sorry about it. I hope that I met you on the first day, the inauguration day, so you know me who I am. So we'll start with this one, and I think I have already. I'll pass through this lecture, the slides quickly because I have already talked to you about these things. I'm not so sure whether I talked to you about all the things here. So we'll pass this one, and the other thing I have to mention here before starting that there is a submission in your activity calendar. I saw that there's a submission due on 20th, right? To do that, actually I have not put the assignment yet, but I'm going to put it tomorrow, so that I'll give you a few more days and I'll put the link also, a very simple one because the material, lecture material, one lesson, the whole lecture materials are available in the LMS, right? I hope that you can do follow through. And if you actually speaking, it is not that we are giving you lectures. It's kind of a kickstart that I'm going to give you because at the beginning, from the beginning, we told you that this is something that you have to do on your own. If there are things that we have to explain more, then we can do it by arranging some help sessions or some lecture hours, and it's up to you to do all the references or go through all lecture materials available in the LMS, right? It's completely full now, but I have open only one lesson material. I'll do it once we finish the first assignment. I'll open the other one so that you can follow it and just refer some material. And if you have any questions, you can post it to me. I'll open the discussion forum also, or the link there, so that you can put whatever your problems in that link, right? Okay, you can disturb me if there's any problem of hearing or seeing the screen. Okay, so before moving into the subject matter of this thermal energy or this energy conversion technologies, uh, uh, just let us look at what we have already gone through. I think you can remember this one. I told you that there are 11 out of 11 courses, 4 from University of Peradeniya, and this is one of the lectures. And the lesson 1 is power cycles, if you remember what I told you that day. So power cycles, its complete lecture materials are available in the LMS, right? So you know where the LMS is, you go to LMS and then you go, this will be the course page that you can see in the LMS. And here how these are actually not so necessary, but you can go through all these things. If you don't understand anything, then you can ask or clarify your problems, right? Here you have this course content. You may see that the synopsis or the course content we agree with at the beginning. We had a fourth lesson as hydrogen energy. Wait, I can't remember the name also. It's something to do with hydrogen. Mm, one, but we have removed it because you have one full course or course unit about this hydrogen technologies. So we will talk about something else in this one as waste heat recovery. That is again some kind of a conversion technology. Energy conversion technologies can be applied there. So we'll talk about waste heat other than instead of hydrogen technologies, okay? Hydrogen technologies and fuel cells, if I can remember the thing. So we'll move into the next one. I think you can see this one. This is how you see the course page and the lesson 1, the power cycles. Do you want me to put the, can you see the cursor? My
Yes, ma'am, I
arrowhead
can see.
moving?
Yes, yes.
Yes,
Okay,
madam.
okay. Okay, no problem. So here lesson 1, you have power cycles and all the modules here. I have given you the 6th one. I think you can, have you just gone through this or have you just tried to open this one of these?
Yes,
I
madam.
hope you must have done it, right? So let me know if that, if you cannot go to the links provided here in the LMS, right? Okay, I'll here there's a Zoom link for discussion. I will actually not a Zoom link. I'll put a forum here so that you can post your questions if you have any thing to clarify. And if you go to the learning outcomes, I don't want to tell you all these things again repeatedly. I think I have already told you about these things. So we'll move on to this one. Now here you have the first one, the power cycles introduction. You have all these things. How do you, or you see this link, if you go to this link, you will find something like this and you have this arrow here. You can go to the next one and proceed from there, or you can see the course material or this introduction to power cycles. Inside this, it's kind of a video, not really a video, but you can go to slide by slide and see what is inside and then go to learn about the basic concepts, okay? So then moving on, here I think I have told you about these things also. In this case, I think sorry, just let me look at what this chat is. What is the assignment submission date? Okay, I will put, I'll let you know in a while, right? I mean, once I finish this one, I'll let you know about this assignment and also the link to or the submission link, okay? So here I think I mentioned all these things. Now the people who have or who don't have any basic knowledge in thermodynamics, you may have to refer little bit more from there are references given in that. So you can see how these things are very simple things. When you come to advanced things, then you will have to have, you may need to have more help. In that case, you will have to tell me, or you can get together and find out what else to do to learn more, okay? The laws of thermodynamics and basically, or importantly, the second law of thermodynamics, you will have to learn it very carefully and how to apply them in the conversion technology. So whatever the problems that you come across, okay? And then, so this is, now I'm not sure whether I showed you these things. Did I? Did I explain you to these things in the first introduction we had sometime about a few weeks back? Hello? Hello?
You showed them, madam, but I'm not
I
sure.
didn't explain. Okay, I will go into them separately. So somebody has to answer. Otherwise, I will I will think that because I told you my computer is not so good. So I don't know whether you hear me or you see me see the screen. So quickly answer, right? Yes or no is enough. Okay, I'm not going to ask you technical things here. It's kind of a friendly discussion. So you can ask me anything and answer quickly so that we can save time, right? And it is after a heavy day maybe for you, for me also. So we are spending time. So get some serious input from here because I mean we are spending our valuable time here, right? For you, of course, it's very important. You are paying for it. So please take some interest to learn more. Okay. So here about this gas, when you talk about these power cycles, as I told you earlier, we have two cycles that we are going to talk about. Steam power cycles. You know, steam is some kind of it has lot of energy, steam. So we use them in certain to run certain machinery so that what are the things that you have to learn about these steam properties. So usually in any machine working in a cycle or working in some kind of a process, so you need to learn, we are talking about them here as power cycles, right? So we'll see what are these power cycles are when you talk about steam. That is one kind of a fuel or one kind of a energy source, and the other one is gas power cycle. So what gas is, again you have to learn about the properties and how they work, how they change their properties. Now these are very basic things that I am telling you now, right? So gas and steam power cycles you will have to learn, or you will have to go through them carefully so that you will not miss anything because they are kind of changing its properties, right? So these changes give you certain kind of uh, power output or some energy output or whatever the things that we are getting as a secondary source. The first source will be a fuel, and then we use a machine and to uh, convert them into a usable form. So that is where we have this conversion technology. You have to convert it to this primary source, convert it to a usable form. We need technology to convert the to do this conversion, right? In that scenario, that is how we use the steam power cycles and gas power cycles. And you can see here also in the basic difference or the main difference in between these two are the steam actually it changes its phase during the cycle. One part it will be a liquid, water, steam produces from water. So one phase it will be water, the other phase is saturated steam or superheated steam, right? That is vapor. But in the gas, when you talk about gas, it is the main difference from the steam is that it doesn't change its phase. The gaseous phase will be there throughout the cycle. Okay, this working fluid will not change its phase, but in the steam cycle it changes the phase. Now this is one thing, the basic thing, the first thing that you need to understand. And we'll talk about how these two work. When you say cycle, uh, it can be an open cycle also, where somewhere there's no connection between the input and the output. We say it's an open cycle, and if there is a connection between the output and input, we can say closed cycle. We'll see how they are, right? And other than these two, we have heat engines. Now these heat engines, of course, I'm sure that you know what this internal combustion engine is. It's in all certain, again, some power produce engines, and also external combustion engines also there. So we'll see what these two are. Then vapor power cycles and the laws of thermodynamics, as I said. And if I go to this one, now I told you there are two cycles we talked about, and two classifications, open and close. Now you can see from here, now this is a gas power cycle, or gas schematic. Actually, the gas plant schematic. When you say compressor, when you say turbine, I hope you know what this compressor means and the turbine means. We'll see what they are, right? Combustion chamber is where the fuel ignite and give some power. Of course, you know power means some kind of a heat that you are using as to turn some turbine, or to convert it into electricity or whatever. It's kind of a open cycle, but here you can see, and I'm not sure whether you know about this temperature entropy diagrams. People who do thermodynamics, they know about these things. Can you tell me whether you can whether you know about this temperature entropy diagram? In the usual notations, temperature is T and S is the entropy. I'll tell what entropy is little later. And then here the steam schematic is also same. You just cannot use water directly into this. You have to pump into this one. I mean, you have to elevate the pressure a little to go into the boiler, and then have the ignition. Then you have this in the turbine. You have this cycle. I'll explain what this thing is a little later. So hopefully, I think that you know about this one, right? The TS diagram, we'll see. Okay, the next one will be internal combustion power plant, and it's you can see the content in it: combustion engines, internal combustion, reciprocating IC engines, and parts and terms. Then the working principle, pressure volume diagrams. Now I have written this, or I have indicated this here in red color, meaning that you have to that is the most difficult part for the others who doesn't know anything about this mathematics, or about the not anything about basic physics, right? These two and the analysis you will have to carefully learn. Other things, of course, they are just like stories. You can go through them, and they are like kind of a story. You can read about it and find out how they work here, right? Okay, so then next is advanced steam power cycles. There again you have this lesson 2. We'll go into that little after this, finishing this lesson 1, because you have 6 modules there. I think you have enough material to study. So I will open this one, the lesson 2, in at the end of this month, or I'll think about it, right? Because lesson 1, you have enough things to go through. Please go through them, right? That is up to you to do all these studies. If you need any clarification, I'm repeating several times, you need to contact me and find out what kind of what is your problem, and whether I can help you in that solving the problem. Okay, solving the problem in the sense not working out all these mathematical things, but at least how or to where to go or what is next that you have to do. Okay. Then this I told you, if you go to YouTube, you can find out a lot of YouTube videos to learn about all these things. Please go through them, and I will go to the lesson, right? So this is about what I have already done. We'll share the other one, and I'll start that one, right? Stop share, and I'll share the other one, okay? All right, so let's move into the power cycles and what can we do? Okay, same theory. So, okay, now we are going into power cycles, okay? The basic stuff. I will just summarize, or I will just, this is not a lengthy or a very elaborate lecture or this lecture material, but you can find all these things in the LMS. So I'm just going through, or I'm just covering some basic stuff here so that you can continue with your studying, right? I mean, learning activity. So, power cycles, actually, I told you about this steam power cycle and gas power cycle. That is, you can see here, I have written here, the devices or systems used to produce a net power output are often called engines, and the thermodynamic cycles they operate on are called power cycles, right? Now, when you say thermodynamic cycles, that is, we have to talk about pressure, volume, temperature, and heat values. They are depending on temperature sometimes, and we talk about lot of assumptions in this case when we want to analyze these cycles. Those things also you should clearly understand whether to have an assumption or to analyze with the basic stuff, or analyze it very up to the point where it all changes incorporated into the analysis, right? There are always, we just cannot do it exactly 100% accurate, because always these conditions may change, right, due to certain other things also which we cannot actually sometimes incorporate. So that is where we keep just a margin, and then we analyze, okay, we assume this kind of margin, a safety margin, and then we say, okay, we can do it like this, and this will be something roughly about this much. But when you go to design stage, it will be more difficult than what you see here, right? So here then it says in gas cycles, we'll talk about them in detail. In gas cycle, I told you the working fluid remains in the gaseous phase, but in the steam cycles of the fluid, or this vapor, it changes its phase into liquid phase and then gaseous phase, okay? And thermodynamic cycles, I told you, there are categorized into two categories, like closed and open cycles. In closed cycles, the working fluid is returned to the initial state, and at the end of the cycle, and it is recirculated, okay? Now remember this one, when you say closed cycles, once you finish it, it will come into the initial stage, and in open cycle, it will be not recirculated, but it can be renewed, right? it is renewed, not return, it is renewed. That is, you have to give fresh fuel into the system so that it will continue the cycle. Okay? I hope you understand what I say. Right, let's move on then. There's another chat. Okay. Somebody is asking the first class. This is the first class actually. We just introduce how this course modules or LMS is about, and this will be the first class that you are doing. In that scenario, again I am telling you, this is not really a lecture, but I'm giving you a kick start, where to start. Okay, right? All right. No
Okay,
answers, right?
madam.
Yeah,
Yes.
sure. Okay. So now I told you about this one. Let's move on. So now I have given you a few bullet points uh, about this power cycles. Uh, so it is I don't know whether I have to read about this one, but anyway, I'll tell you. I just told you that the power, the engine produce power, and the working method is undergone with these thermodynamic cycles, right? And power cycles, two categories, that is steam power cycles and gas power cycles. In the gas cycles, the working fluid remains yeah, as in the gaseous phase, but in the vapor cycles, it is changing its phase. Part of the cycle it is as a liquid, and part of the cycle it appears as a gas in the sense vapor, right? So and also it can be categorized as open and closed cycles. In the closed cycles, the working fluid return to the original state, but in the open cycles, it is renewed in the at the end of it, right? We'll see how that happens in the when you talk about internal combustion engines and this gas and steam power. I hope you know these two cycles. It doesn't change into the whole thing doesn't change into the initial stage, right? So and there are two engines in the heat engines category. They are categorized as internal and external combustion engines. In external combustion engines, that is, this external combustion engine is you ignite or you produce the energy in a boiler uh, from a external source. But in internal combustion engines, you know, in these vehicles, it is different, right? We'll see how they are when you talk about more in the lecture, right? Or in the study material. So, and as I just indicated here, in internal combustion engines, the energy supplied by burning the fuel within the system boundary, you know, it's burning inside the cylinder in this kind of a cylinder in internal combustion engines. But this external combustion engine, you have to change the state where the fuel can be ignite. I mean, you have to increase the pressure, you have to increase the kind of volume or decrease the volume. And then you supply a burning method or some ignition outside the cycle, outside the engine. So that is we call external engines, external combustion engines, right? So, and you can see steam is the most common working fluid in vapor power cycles, and that is because it has when you have superheated steam, it will give you more energy than any other uh, fluid. Okay, so that is why we have this one. So steam power is used in coal power plants, nuclear plants, and natural gas plants. I hope that people are here in the power industry, and so you may know how these things are utilized. We'll look into more details If you want more details, I can provide them. Like, I mean, if you are in the power industry or this generation or whatever CEB, there are people in the power industry, right? It is not, there are people again in the renewable energy industry. So a lot of people here, it is anyway, it is energy. So we'll see how you can incorporate your advanced learnings into your working or your career, right? Right, okay. Now these are the things that you have to remind or recall. The people who doesn't know about these things, please read about them and learn about it, right? The zeroth law say that if there are two bodies, they are in the thermal equilibrium. Now I hope you can understand what thermal equilibrium is, right? If one body is heated and the other body is not in that temperature, they will come to equilibrium state. That is obvious, right? And it's a very common thing that you can think about. So it's, we say it's the zeroth law of the thermodynamics, right? And so I have here I have given you two ways here also. You can see two bodies have equality of temperature with a third body, then they in turn have the equal temperature with each other, right? And or else you can say two bodies are in thermal equilibrium. If both have the same temperature, then they are not in contact. Okay, so this is these two are a little bit different explanations, but it says the same thing. Okay, the first law says that energy cannot be created or destroyed. Obviously, the energy content inside a kind of a source, it cannot be destroyed also, and you cannot create any energy also. It has something, you have to change it into a certain other usable format. That is what says in the first law. And the second law, of course, I have not written here because that is where we use a lot of things in the second law. So let's go into that one. These are things that you should know, that there are laws of thermodynamics such as this, right? And you can see the third law says it is impossible to reach a temperature of absolute zero. There's no no temperature called absolute zero, but you know it is usually we call absolute zero. T is equal to 0 Kelvin. Okay, that is in the Kelvin temperature scale. Now these are bit of basic stuff. I hope all people who do science in primary classes up to grade 10 know about these things at least a little bit. Okay, right. So here, now the second law. We are coming into the second law. Now this is what we should know properly. Learn this very carefully and understand the basic, and it is the very important concept, right? Heat engines, you can see here, heat engines receive kind of heat, and then it gives you heat out. Okay, heat out from this source you take into the heat engine or use it kind of in a heat engine, and then it sinks out to a temperature, low temperature sink, by giving you some kind of a work output. Okay, hope you can understand. So when you talk about this heat engine, okay, second law, there are two statements. One is Kelvin Planck statement, and it says it is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a lower temperature body to a higher temperature. Okay, now read this and understand. Now it should be from heat high temperature source to the other one. Other way it cannot be done, right? The work can be converted to heat directly and completely, but converting heat to work is not as converted heat. The work converted into heat can be done directly, but the other way it cannot be done without a device. That this device is the heat engine, what we call. We have the kind of heat here. We have to have an engine to take some work out. Okay, so this special engine is there for you to take the work output from a heat. Got the point? Okay. The fraction of the heat input that is covered to network output is a measure of the performance of the heat engine. Now that is called thermal efficiency, and it is obviously the thermal efficiency is something the network output, that is Q in, you have some Q in, you have some Q out, and from this how much you have taken out is the efficiency. So you can say the work output is this much, and from the heat that you input to the system, and you have taken some work out from this engine. So that is what you call the thermal efficiency, and this can be expressed. Now this is the Carnot efficiency, if you can remember. The high temperature source and low temperature source is here. So that can be the Q heat is actually a measure of heat can be measured using the temperature values. You can talk about a kind of temperature, and then you can say, okay, this much of heat can be derived from this source at this temperature. So that is the Carnot efficiency. We usually call this Carnot efficiency. So that is the basic thing that you have to understand in these things. You have a high temperature source, you have a low temperature source, and you have a heat engine in between and take some work output. So you have the can calculate the thermal efficiency. Okay. Right. Now this is what I told you, this reversible process. You can take the system and then you can take some heat out. You can see the system undergoes some change such that this system plus the surroundings can put back their original state by exactly reversing the process. That is how you call this reversible process. But in the other hand, I told you the changes proceed in infinitesimally small steps. You cannot at once you cannot convert it. It has to be in little steps, so that it come to the equilibrium in each state. Now this is some kind of a phenomena, a very common phenomena that you can even imagine, right? I mean, you cannot completely take a high temperature source into the low temperature source. So that is how you talk about this reversible process. In the other way around, it should be very slow. Now, not like in this case, right? Not like that you add heat and then you go into the temperature equilibrium state, but here you have to reduce the temperature. It is very come to equilibrium, it should be very small, but anyway, if you come to the original state, you call that process is a reversible process. Now these are things that you have to learn in your basic thermodynamics. Okay. Then let's go into some processes with some specific names in it. That is, you can talk about when you say in this heat transfer processes or this the temperature involved processes, you can talk about isothermal process. Now you can see isothermal, the word implies that the temperature is constant. If you have a kind of process where the starting temperature and the end temperature is equal, we call them that process is a isothermal process. And you call this adiabatic processes that the pressure is constant. Now I told you at the beginning, we talk about three things when you talk about this gas or a liquid. We talk about pressure, volume, temperature. You remember in your school days, up to grade 10 science, you learn about this Charles law, Boyle's law, and certain other laws which include this temperature, pressure, and volume, right? I hope you can remember them. And when you come to A level class or come to after a degree program, some people might have gone a little far from there, but then you will have to, others have to, please, people who know about these things, please help the others to at least understand this basic stuff, okay? Right. So we'll go into the next slide. Okay, now we are going to learn about the steam power plant. Anything that you didn't understand about the things that I talked to you now? I think I talk little bit fast. So if you, I mean, cannot go through, please let me know, right? Okay.
Okay.
Yeah, sure. So now we have the steam cycle. Now I told you, you just cannot to have some kind of a steam out from this boiler. Boiler is something, a closed vessel that you know, where it generates steam, right? And I hope that you know, wait. Oops. Okay. So here, these diagrams, okay, for water, you have these diagrams and you have kind of temperature and entropy, and then you have some pressure lines, some, these are pressure lines. When you have a certain pressure and temperature, you have a specific volume in it, and you have a specific entropy in it. So you have to find out a steam table, or else now here some ideal gas properties, that is air. You can see the temperature is there, enthalpy is there, internal. Sorry? Sorry? What was it? The same examples like I see engine, you explain, make it. I'll do it later, right? Okay. Yes. There are two chat in this saying that up to 1.6, yes, the first lesson only visible in the LMS. I will give a assignment on these power cycles, and then we'll go into the second one, right? And here again somebody says explain about the processes. Okay, I'll do it in a little while with this one. Okay. So be happy. My computer. Okay, so this is steam tables. I hope that you can. What happened? This you call usually this Mollier chart. You can see here the enthalpy, because at a stage of steam, when it has a temperature, specific temperature, or a certain temperature and pressure, it has a inbuilt enthalpy, that is the energy, right? And you can see that it is kilojoules per kilogram. Oh my god, what happened? My computer giving some kind of problems. Okay, let's go into the beginning again. Okay, we were here. Now see, you wanted me to explain this one. Now in the steam process, in the steam cycle, or in a steam engine, we have these four items. A boiler where you put the heat in, and then the turbine where you get the work out, and once you take the work out, there should be some low temperature sink for the remaining thing to condense, Now we are using the steam now. Was some part of steam, we use the enthalpy to take some work out, and then the exhaust will be, the steam will go out in a different stage, and you will have to have a condenser to condense this steam into water. Now that can be gone into the pump, and you can pump that again into the boiler, right? Now to work this pump, work out this pump, you have to supply some work. Then only it will, once you give some work in this, the water or the steam, the water will rise it pressure, so that you get into this boiler some kind of a elevated pressure steam, so that it will give you, once the burning or this, once you supply some heat, it will increase the temperature and the steam will go into a superheated or heated stage. Now when you talk about steam, you can talk about the saturated steam, that is water and vapor in equilibrium stage, and only vapor. You can increase the temperature up to a certain level, and that will give you different stage. We call them superheated steam. This superheated steam at a temperature, certain temperature, beyond that temperature you can increase the temperature with the pressure, and that will give you kind of changing enthalpy or more energy, right? So that is how this steam engine works. Once superheated steam go into the turbine, of course you should know how this turbine works. It has blades, it will rotate. Once it hits this and with the energy, it will rotate the shaft and it will generate, or you can take some work output. Usually we can convert this into a send this work into a generator to generate electricity. Now this is the basic cycle, and if you talk about the net, W net, that is here the W net, or what is the work output that you are taking, that should be something work out, that is we take this one, but here we are giving some work into the system also, so it should be work out, but you have to reduce, or you have to minus, or you have to take this work inside, because we are giving some work to take some work out in this system, right? Q in and Q out also the same. You have to produce some steam, and here also once the condensation is happening, you giving some heat out to the environment, or some kind of a maybe some other equipment, okay? But usually I told you the first law says you cannot destroy the energy, or you cannot create energy also. So this internal energy is not changing, so that goes to 0. So it is Q plus W, and you can say Q is equal to Q in and Q out, and here it is W out and W in. Now this, I hope that you can understand what this thing is. So here you can say, if you take this out, I mean take into this one, you can say Q in minus Q out is equal to W out. Now these are usual notations. Please remember that when you talk about W, we talk about, I hope that you can remember your basic units and standards. So we have certain standards, and we have certain notations in given in this IC standards or SI system. So in usually we for to denote heat you use Q, to denote work you use W, right? So the performance or the efficiency is the desired output, and what you need to take that output, that is the required output. So you have to find out here. In this case, the desired output is W out, the work output, and the required input is what you supply into the system here. These are things that you have to subtract from the heat and work into the system and out to the out to whatever the work we need. Okay, so as I told you earlier, the Carnot efficiency here is described in Q out and Q in. Now, why this Q Carnot efficiency? We talked about temperature, right? We have, that is the ideal situation. If you have the temperature in a certain fixed level, the high temperature and low temperature, the Carnot efficiency is that high temperature and low temperature relationship, as I told you, 1 minus T L minus TL over TH, right? Remember? But here Q is different. Q is the heat input. You have, if you have your working fluid here, that has a heat value, right? Kind of a volume or mass going to this turbine, or from here you have to take that into account, and you know the heat value you usually call about Cp or Cv, remember them, or the heat value here. In steam, we are not talking about this heat value of Cp and Cv, it is the enthalpy. Usually Q is equal to m delta H, remember? I am not sure whether I am giving you kind of the people who doesn't know anything about this enthalpy and heat values, you may have to read a lot. Okay, Rishanti, I think you know you are not from science background. Am I correct?
Yeah.
Rishan.
Yeah, ma'am. Not.
So maybe Greek to you. Huh? So you
Yes, some things, yes.
okay, but anyway, the basic things that I'm telling you, I hope that you can read about enthalpy and other properties that we are talking about in a working fluid, that is gas and steam, right? Then you will undergo, or you will find out that these are the properties that it changes. And when you talk about heat value, that is when you in a gas, it is m Cp delta T, but in steam it is m delta H, right? H is the enthalpy. The notation for enthalpy is H, the notation for temperature is T, and these two notations I just told you. Okay. So now this is the steam power cycle we talked about earlier. Here I told you this is the schematic of a steam power plant. Then you go into the system. Here you can see that you have a turbine here, and you take you take the work out from the turbine, and you have the steam generation here using Q in is some kind of a material, say maybe coal, maybe uh, petrol or diesel or something like that. You have to somehow give here some heat input to generate steam, right? So this color indicates at this level it is water and it generates little steam, and then it goes to red level, in the sense it is superheated state. That is about this temperature and entropy diagram. You can talk about the ideal cycle if that is in a two temperature levels, but it is not that. So you have to find out what is this Carnot cycle put into the steam power cycle, right? Now steam power cycle, the working fluid of the cycle is water. The water is pressurized from lower pressure to a higher pressure by a pump, I told you, and that is 1 to 2, and then converted to steam by a boiler here, that is 2 to 3, and then expanded through a turbine that you can see that we expand. Now here the volume is little, but when you expand it, that is the volume, when you say expand, the volume increases, and volume go into this expanded through the turbine blades, because you turn this one, this turbine blades, and it gives you some kind of a expansion, and then rotates the turbine shaft. That gives you the 3 to 4 stage, expansion happens, and then generator, you take some work out here, and then the steam, remaining steam here, the expanded steam here goes into the condenser, where it condenses into water. That is this 4 to 1 cycle. So this is the basic or ideal cycle. But real cycle is not like this. You have to go to again we call it, now this is the Carnot cycle, right? Now here you can see the Carnot cycle. I have given here the explanation in this case. So we'll see what is the real cycle here that we call Rankine cycle. Now remember these names, right? Now these names came after the person who described this in a scientific manner. The scientist who described about these things. So it is Carnot who described this ideal cycle. But when you convert into the real state, it is the Rankine cycle that we are talking about. We will see how it is in the next diagram. See. Now earlier also I told you this is temperature and entropy. Here it is again temperature and the same thing, the entropy diagram. Usually this diagram is there, and these are constant pressure lines. I told you the adiabatic processes, these are constant pressure lines, and then it increases. Okay, sorry, I'm so sorry. This is constant temperature lines. You can see this temperature. These are constant temperature, but the pressure increases, volume increases. You can see the enthalpy also increases. These are enthalpy lines. And this here, this Q in happens in this 2 to 3 stage. Now here I told you earlier, ideal cycle is just a square or a rectangle, but real cycle it is not so. 1 to 2, you have to increase the little pressure, increase this pressure of the water which pumps into the boiler. Here, from here you have to give in some work, and then you pump into the boiler, then you put some heat into it, then you generate the superheated steam with this boiler. You can see earlier I told you this is simple and easy to understand. The same thing that I'm giving you here without any inside details. In the turbine you have this 3 to 4, it reduces its temperature also and goes into this stage. Now this is again some kind of an ideal stage, and we are talking about another property which is here indicated. Now here you can see 3 to 4 and 1 to 2 are straight lines or vertical lines. That is, entropy is constant. Entropy is again a property of this working fluids. Okay, but in ideal case this entropy does not remain constant, but you can assume it doesn't change much. But the ideal real case, the entropy will be somewhere here, it will come into somewhere here. But all these properties can be located if you know temperature levels, or if you know two properties from the diagrams given, the Mollier chart and steam table, you can find the other properties of each and every step of, or each and every point of this cycle. Then you can analyze or you can calculate certain values to find out the performance of the steam engine. Got the point? Okay. Move on here. The energy analysis of a Rankine cycle. Now see what we talked about in the steam. We are talking about this enthalpy. Okay, 1 to 2. Remember, this is usually a common diagram. These stages, when you say 1 to 2, in this that is referring to pump. 2 to 3 referring to boiler operation. 3 to 4 referring to turbine operation. 4 to 1 again referring to the condenser operation and going back to the initial stage, right? So this goes as a closed cycle. You can see it. Temperature also increases while inside the boiler, and it increases the enthalpy as well. So it comes to the stage 3 where it enters the turbine and expand through the turbine blades and then give some work output. While this expansion happens, this rotates and it will give you a work output. Now see, actually I should not explain this in this detail if it is only that you have learned these things basically in the undergraduate stage. But here I'm taking lot of trouble to tell you basic things because here it's a wide variety of basic qualification applicants. So you will have to, you also will have to put some effort to understand how these things happens or how these analysis is done. You may not use them in your workplace like this kind of analysis, but you should know how it happens. Okay, that is why we are taking all the trouble to tell you, okay, these are the things that you should have in your vocabulary or in your knowledge tank so that you can use it any time that it is necessary. Okay, so here again the energy balance I told you, internal energy does not change, but the enthalpy change, right? It is this one, and you can see this enthalpy change happens for the pump. It is H2 to H1. So this is the same stage and the notation enthalpy is H. So if you can locate these properties from the tables or from the Mollier chart, then you can have all these values. If you know this temperature and the pressure maybe, you need to have two properties of a substance to locate the other properties. You can locate any property if you know two of the properties, either pressure, volume, entropy, temperature, enthalpy, or whatever the properties that we define. Two is enough, two are enough to locate the other values, right? And or the specific volume, okay? Now in this turbine or in this boiler, you will have to be very careful because it starts from water and then it goes to a superheated steam. If you go to tables, I'll show you that. So this is actually simple calculation with the or simple explanation how these things come in. Enthalpy, here enthalpy you can define with specific volume and pressure. That is, you know how it is created from the basic laws of Charles, Boyle's and the early things that we learned, right? When you talk about H2H minus, or else you have to talk about specific volume and the pressure, right? Q in is also, Q out is also the same. If you know two properties of this stage, then you can find out other one. If you, again, same here, all four stages, you can locate them from or locate the other subtract or extract other properties if you know two of them, right? So you can talk about this thermal efficiency, that is network output, and the fuel input that you give in here or the heat input that you give here. So here W net is equal to Q in minus Q out, that we basic thing. So you once you calculate this one, you can just if you know what is the Q in or what is the Q output or else what is the work output and Q in, then you can calculate the thermal efficiency of this plant. That is the indication we talked about in a plant, the efficiency, right? And you have to know in a steam power plant, the efficiency is only about it is less than 30 actually. It is very difficult. But if you talk about gas turbine and combine gas and power, gas and steam, that will give you more than 50, right? Then we will talk about combined cycles little later. Before that, we'll learn about steam separately and gas separately. Then now here, I told you that the entropy changes in the real situation. But what we do here is we idealized or we assume certainly in certain instances this entropy does not change. Then only this 1 to 2 is a straight line, and 3 to 4 is also a straight line. This is also a straight line. But in reality, you can imagine when you supply some heat, it is not remaining at a stage where the temperature is constant, right? So the ideal cycle, the real cycle or the actual cycle is a deviation from this, but we can assume this constant temperature and constant temperature here and constant entropy if it does not say that it changes the entropy. If the problem says that entropy changes, then you will have to take about this real positions by incorporating the other positions into it. Got the point? So here, if you talk about this again, the isentropic efficiency is when the entropy is a constant. Now you can see that here we talked about the isentropic is the entropy constant position, but the real position, it is, I have denoted it as an actual position. Okay, 4s and 4a. So here you can see if it does not say anything about entropy changes, you can take it as 4s. But if it says the entropy changes in this process, sometimes you will have to incorporate this into real situation. In real situations, you can just think that it is if it doesn't say anything about entropy, you can take it as constant entropy. Okay, got the point? I hope you can at least compromise your this time may be a little bit difficult for you and for me also, right? I have to talk a lot now. So nobody disturbs. So I'm thinking that you all are at least taking some of what I say. May I continue?
Yes, ma'am.
Yes, ma'am.
Yes,
Okay,
ma'am.
madam.
Okay, okay, let's go. So this is now I'm again telling you actual cycle is not that easy, right? You have to talk about real cycle. We derive the Carnot ideal one into the real Rankine cycle, and in that also you have to derive it into changing entropy and changing properties as well. If it doesn't say anything about these changing properties, you can talk about the Rankine cycle as the ideal cycle, not the Carnot one, right? Carnot is very easy, but here it is the Rankine cycle where you have 4 stages in different pattern. Okay. Right. So here the Carnot, I'm telling you the reversible cycle. You can read this one, and I don't have to talk about this actually. This reversible cycle and the efficiency that we talked about all these previous slides. The isothermal expansion. Now here, see, I told you that here in the turbine. At the 3 to 4 stage, it expands. So in this expansion happens in a constant temperature that you can see it here. Okay, but in the pressure and volume diagram, you can see it changes in a different way. Right? I told you about adiabatic and isothermal, what they are at the beginning. So remember this one. At this stage, it is isothermal expansion. Here it is isothermal compression. Here it is adiabatic compression, and here it is adiabatic expansion. You can see when you say expansion, it is increasing the volume. Okay. When you say compression, it is decreasing the volume. Now here this axis is volume and this axis is pressure. Earlier we talked about temperature and entropy diagrams, right? Here it is temperature and entropy. So we can talk about all these things because I told you, if you know two properties, you can locate or extract the other properties from the standard values that is given or that is stated from long time after research and experiments. It is stated in the table. Okay. So they are actually, it has happened after all observations. They have put that into certain tables and standards so that you can take them as granted. Right. So this is the scientist, Kano, and you can see that he has lived only few years, very young age that he has talked about this cycle, Kano cycle, okay, best known as reversible cycle. Read about him. It's interesting to read about all these scientists. Why not go to internet and find out who Plato is, who Aristotle is, who this the great scientists or philosophers, right? It's very interesting. When you have time, read about them rather than the gossips that you have every day. It's very interesting. Not to read about all these politicians, all these actors and actresses, their lives, but you can talk about or you can read about scientists. I'm giving you some kind of a deviation, okay? Read about them. Right. So here now we are indicating the same Carnot cycle in the steam power plant in terms of pressure and volume. See this? In this, when you put this heat into that process 1 to 2, that process is QH. And that happens in a constant temperature. You remember we talk about TH and TL in the ideal Carnot cycle. So I don't have to explain this again. I told you here it is only thing is pressure and volume. The axis to axis are pressure and volume. Here the same thing, Rankine cycle. I'm telling you this. I have already told you about this. So here this you have in isothermal temperature you can heat is proportional to temperature. When you increase the temperature, it gives you more heat. That is obvious, right? So the Carnot efficiency is this one. And once it is talk about all these things, if it is not the Q or the heat input and heat output or work output and work input, then you can talk about this temperature, two temperatures. Thermal efficiency will be anyway the net work output over the heat input that you give into the system. So these four processes, now you have four processes, 1 to 2, 2 to 3, 3 to 4 and 4 to 1. You can simply write it like this, m dot either enthalpy difference or with the pressure difference. P is equal to H here. You have this m dot. Obviously, you will have to have a mass or a volume, right? Because you supply some mass flow rate. Now here dot indicates the rate. So for the pump work, it is m dot into enthalpy difference. For the heat input, it is m dot into enthalpy difference. The turbine work output, the m dot or this mass flow rate into enthalpy difference. So this is so simple, but it is not so simple when you talk about some problems when you don't have enough data. If you have mass flow rate and enthalpy, you can just calculate all these things and find out the efficiency. But it is not so easy when you don't have other properties or when you don't have this pressure and volume to locate the enthalpy. Okay. Right. Now we talked about some entropy. We were talking about entropy, right? What is this entropy? Can anyone understand this entropy? No? Okay. Now we know that we are talking about pressure as a property. We are talking about temperature as a property. We are talking about volume as a property, enthalpy as a property, specific volume, uh, something like all these things, or the dryness fraction, I mean steam content in some saturated vapor. When you say saturated, it has liquid and vapor both, right? When you talk about superheated, it is only the steam heated to a high temperature. What is this entropy? It is again a property, right, which changes according to temperature, or this heat value is changing according to temperature. You can say that it is kind of a property that it changes, or this heat value where it changes with the temperature. Got the point? So this, if you talk about some kind of a entropy here, irrespective of this process, you can talk about these two ends, but it changes in a different way, like an integral. Now you know this changing is not a straight line. If it is a straight line, of course it is all right, but here you can see it is a property. Not always this dq by t is a property, right? It's an integral, and you can see entropy is a property. Therefore, the entropy change S between two specified states is the same. No matter what path is reversible or irreversible, it followed during a process. Whether it is going like this, whether it is going like this, or whether it is this, these two are there, but the changing is different, right? So don't try to complicate things by by thinking that entropy is you cannot understand, but it's simply a property, right? Okay, not always this path is the property, but these two stages are kind of property. Path, you can say any path, it will go into the point 2 or 2 from 1. Got it? Got the point? Okay, whether it is reversible, irreversible or whatever, whether the path is somewhere here, these two stages are there. So it's a property that you can talk about, not the integral, but these two values of this entropy is a property where you can find out from all these things from the tables. Okay. Now see, not always the integral of dq by t is a property. It is not always the same property, but will give us the value of entropy change only if the integration is carried out along an internally reversible path between two states. Now this, if you read about this one, then you can understand what this is. Simply, it's a property, right? So think about it, and if you just look at the Mollier chart, you can find out this one. Now see this temperature and entropy diagram. When you talk about this constant temperature, it is not constant always. You can see the specific volume is changing, and this the pressure lines are here. This one, this is kind of indicating when you talk about water, this indicates the line where this saturated in the sense the water and vapor are in equilibrium state, and this is the critical state where all these things are superheated steam. Now once this pass this stage, it is superheated. You can see that the temperature is increasing, and here again the saturated vapor line is indicated in temperature and entropy diagram like this. Okay, so TS diagrams, you can see constant pressure lines, and the constant pressure lines are parallel to each other, and constant temperature line in saturated liquid vapor mixture region. right? And the critical constant pressure line almost coincide with the saturated liquid line in compressed liquid region. Now this is some kind of a, we call this actually the Mollier chart. You can now this is only one that you see of few lines, but if you go to Mollier chart you will see that lot of lines are there where you can locate any situation when you know two properties. Now see this Mollier chart, temperature, entropy. Now this is the saturation line, ups, and you can go to high temperature things and you can see the enthalpy. Well, we'll see this one. So this is the temperature line. Temperature lines are in the horizontal lines and vertical lines are entropy lines, and these here you can see the pressure lines and the specific volume lines. Okay, here the pressure lines are there. You can see these pressure lines in the sense where you have this whenever you talk about state in this line, the pressure is equal to given value. Whenever you talk about, now these are not things that I should tell, right? Any a small kid will understand, but these lines, if it is a horizontal line in a graph like this, the temperature is constant. And if you talk about the entropy is constant in this way. And if you talk about these lines, the enthalpy is sorry, the pressure is constant. Okay, let's go to a line where somewhere here. So here you can see this is saturated vapor line, and then you can see these, all these things are very high enthalpy, means these are all superheated stage. Okay. So these, if you want to, if we are going to talk about or if you are going to work out some problems, then you will have to refer these Mollier charts or tables, steam tables, to locate the unknown values, right? Here you can see the specific volume lines. Here you can see the sorry, here the specific volume lines, and you have pressure lines, and you have temperature lines. Now here, of course, all those things are a little bit of um, uh, in a parallel state. Now here the enthalpy doesn't change at this. Now there are two other charts. Let me see that. Entropy is quality of energy. Yes, of course, that is what I say. It's a property, and you are talking about some kind of energy input into it. You can see that the enthalpy changes a little, right? So I told you in this diagram. Okay, you understood what it is, right? Because when you talk about this, here you can see, not this one. Here you can see that if you go into a certain little stage, that will be different enthalpy, right? So it's a quality actually. It's and you can locate the quantity also, because you know this value 2n's. Okay, so when you talk about entropy, it's actually the quality, or enthalpy is different. You are correct. And is there another one? Is there any reason to call the peak of TS curve as a critical state? Yes, of course, there where all these three phases are in equilibrium, saturated and vapor and water also, right? So it is a critical point. You, how to explain? Well, I hope you can read about it, and this is what I can explain. That's a critical stage, because you can't, I mean, have a kind of, okay, it went. Okay, this is the critical state, because you have in this, this is water and vapor saturation, and once it is come here, it is all three in equilibrium, but here it's only the vapor that has a superheated vapor, right? This is saturated vapor, and this point, because it changes its properties the temperature and entropy changes from this point, the quality changes. That has a, so this is the maximum point where you can find out all these three in equilibrium. Okay. So about this I told you, and you can see the air properties. Now this is not steam properties, you can see it is properties of air, ideal gas, right? Not steam. You will find out steam table also something like this. When you have temperatures and pressures, then you have other properties according to two properties, right? Now this is not steam. This is I just want to show you the standard values that you can find out, or the available sources where you can find out all these values, right? And okay, isentropic in steam power cycles, again you go to isentropic compressions. Now this is isolated events. We have a compressor, we supply some temperature, some pressure, certain say gas or something to the compressor, gas into the compressor in a low pressure, and while compressing it increases its pressure and temperature both, right? Compress means you are reducing the volume. See, you go to a pressure volume diagram. If you go to pressure volume diagram, you can find out. Now this is isentropic compression, where you do the compression but the entropy doesn't change. That we call isentropic. You can find out the pressure because the pressure values go in the diagram something like this. Temperature entropy diagram, and you can see how you can derive these two when you know the volume change, because you compress it then volume should change, and the compression ratio you can talk about the ratio of volumes, so you can find out. Now this is this I just put here to for you to understand what this pump and how this pump and compressor work. Okay, pump is compressing the liquid, but in the compressor it compresses the gas or a vapor, right? So here it is the ideal case, that is isentropic, and here it is the real case. It is not 1 to 2, but it is 1 to 2 here. Now it changes the entropy. You can see even in the compressor or in this TS diagram for steam, there again you have this compression. In this real situation, it changes the entropy. Sorry. Okay, so this actually I just put for you to understand between two, sorry, two pressure, because here temperature and entropy, and if you know the temperature and entropy, you can locate this on the diagram, the pressure line on the pressure, constant pressure line, and then you can find out what this is. And in the process also you can find out other things, because if you know the last stage, then you can find out the other things as well. So just for your information, I am giving you this. Shall we stop at this point? Or may I go through this quickly? Gas turbine also. Okay. Gas power cycles. Now we talk about steam power cycles all this time. Here again in the, what do you say? Can I continue? But I think I have lot of slides here, right? Well, we'll see what we can do here. Okay. So gas turbines, it's different from the steam turbine. I told you, you have a compressor here, and then you have a combustion chamber, and then you get the turbine. Again, you expand the thing, right? Expand the gas. You compress the gas first, and then you the compressed gas is ignited or supply some fuel, and then you take it into the turbine to expand, so that you get the products out, right? From the turbine you get the work out, and from the compressor you have to give some work, and in the combustion chamber or in the heat input stage, you give some heat into the thing. You can read this one. A simple gas turbine system consists of a compressor, compression chamber, and a turbine. The working fluid is gas, and gas turbine, in the sense gas, air is again the gas, right? When you take the fresh air, that is, we talk ideal gas. Environmental, the fresh air is, you have so many components in it, but you compress it to a certain value, and when you have a kind of a fuel and air in a ratio where it can ignite, and then you supply some heat, and then you change the phase of this gas into the turbine by just by just turning in between these blades. Then you can take the power output, and exhaust will be out with the products, exhaust products, right? Here you can see the fuel is sprayed to the compressed air, and energy of the compressed air increases due to combustion of the air fuel mixture. Now this is obvious, you have to have fuel and air in a ratio mixing, and then you give a ignition. It will give the energy that needs to rotate the turbine shaft, okay, or these blades. When it is rotating, you give out with the shaft some work output. So that is what you take from the gas turbine. See the gas turbine. Now, when you talk about gas, not like steam, you will have to have some standards or some assumptions, right? These are called air standard assumptions, and there's another one called cold air standard also. So you see, now these three is very easy to understand. Gas power cycles, that is spark ignition engines, diesel engines, conventional gas turbines, all these things are, the working fluid is gas. That is one assumption. Air standard assumptions. That is one assumption. In these engines, the working fluid is gas. And all these engines, energy is provided by burning the fuel within the system boundary. Right? That is another case. Inside a system only, you burn this fuel or this air fuel mixture. Then working fluid air mainly contains nitrogen and hardly undergoing any chemical reactions. Now, any chemical reactions happening inside, because when you talk about environmental or this fresh air, you have a lot of components in it, right? Oxygen, nitrogen, hydrogen, so many sulfur, maybe all these things, it's a composition. But usually you talk about this, it is mainly nitrogen, it is 79% nitrogen. So that is what we take as the working fluid, right? So it doesn't undergo any chemical reaction inside the system. It just compressed and then ignite with the fuel and then expand in the turbine. And the cold air assumption, now these three are just air standard assumptions, and another assumption is there in the cold air, we call it cold air standard. Now these things you should understand, and you have to keep in mind also, because this is not rocket theory. You can see it is very simple thing to keep in mind. So working fluid as air behave as an ideal gas, internally reversible cycle, combustion process replaced by a heat addition process by an external source, and exhaust process replaced by a heat rejection process. Now this is what 4 processes mean in a gas cycle. Okay, and it says that it restores initial state of working fluid. Specific heat values determines at room temperature. Now, this is very important. The specific heat values determines at room temperatures. Okay. If the temperature changes, the specific heat value changes. I hope you can remember your basic sciences. We in our school days or in the basic science, we learn that Cp and Cv are constant values. But this Cp and Cv changes according to the temperature, and there again you have graphs to find out this one. According to temperature, you have to find exact value of Cp and Cv if it says so. If it doesn't say, you can assume that it is the specific heat values are taken at room temperatures. Okay, so that is cold air standard. You have to remember this very well and keep it in mind if I ask you to write these things, because they are very important when you analyze the gas power cycles. Now we go into compression stage, right? Compress means you take some air in a certain pressure and then you reduce the volume to you have a volume. Compress means you compress it to a smaller volume. In that case, to compress the volume or to reduce the volume, you have to increase the pressure. That you can remember. If you remember this process, PV to the power equals PV to the power K equals constant, and here you get T constant, PV constant. You remember this if you remember your mathematics, this analysis or the behavior of this one is integral specific volume with respect to pressure change, right? Pressure changes from 1 to 2, and we call this, there are 3 compression stages we are talking about. One is isothermal. Isothermal work is the temperature is constant, and the polytropic is this n value here, this k value is equal to or it in between 1 and k. When n is equal to 1, we call it isentropic, that is entropy is constant. Now here you see this is pressure and volume. Okay. Now this gas in gas cycles, you have to talk about these 4 cycles: compression, expansion, and other 2. We'll look at it in another small in the next slide. Here, gas power cycles. Now again, there you have actual and ideal. Spark me. I will stop at this point rather than talking. Do I have to? Oh God. I'll go to this one, right? Internal combustion engine. I'll keep that for a while because they are diesel and auto. Okay, we'll go into this one. Gas power cycle. Okay. Gas turbine cycles. Now here I told you this compression, combustion chamber, and then the turbine. So here, if you close this, and obviously once you burn the gas, compressed gas, it gives you, or once you expand this one and this combustion process give you some exhaust which will be in very high temperature, where you can use this temperature exhaust, high temperature exhaust in a heat exchanger, so that you can heat compressive the air intake into the compressor, and you can reduce the work into the, because to compress we have to reduce we have to give the work into the compressor. From the turbine we take the work output, but for the compressor, like in the steam turbine a steam cycle, as the pump needs some work to increase the pressure, here again to increase the pressure you need some work, you have to give some work. You can see here the as we talk about Rankine cycle in the steam case, here it is the Brayton cycle you are talking about in this gas cycle, right? And when you talk about, when you indicate this in the pressure volume diagram, it's 2 to 3 process, the pressure is constant. And 4 to 1 also, you take it as pressure is constant. But when you talk about temperature entropy diagram, from 1 to 2, you increase the temperature, and at that point you increase your pressure and volume in a process where PV to the power K is equal constant. And here again, 3 to 4, you expand the combustion product in a manner that PV to the power is equal to PV to the power K is equal to a constant. Okay, so you can imagine, or you can understand, now this is simple as it is because the pressure is constant. You can talk about PV is equal to something, right? But here it is not that, and we talked about this 3 stages also earlier. The isentropic expansion, isothermal expansion, and polytropic expansion or compression, right? So here you can say Brayton cycle made of 4 internally reversible processes again. 1 to 2 is isentropic compression, and at that in that case temperature is a constant, that is PV to the power K is equal constant because temperature is a constant. Okay, 2 to 3 is constant pressure heat addition. Now this is where we put heat into these 2 to 3, we give heat. So it is constant pressure heat addition process. In the cold air standard and in air standard assumptions, we told you, we talked about this, how this heat is put into the system. Okay. In 3 to 4, again the expansion process happens. Again, it can be isentropic, isothermal, or polytropic. Depending on the K value, we can talk about these 3 stages when you talk about compression and expansion both. Now see these 2 diagrams, how it is indicated. Even though you put a heat exchanger here, the Brayton cycle or these 4 processes remain the same. Okay, constant pressure heat rejection process. You can see it from here, that you reduce your the heat is put out to the environment or to the heat exchanger. Okay. So here the same thing, uh, the simple ideal Brayton cycle, like in the steam cycle. Now this is ideal case because this entropy is constant, but here again you can talk about changing entropy so that it will be the real case, but usually we take this as in this uh, ideal case, right? Isentropic compression, constant pressure heat addition, isentropic expansion, and constant pressure heat rejection. So in the PV diagram, you can put it like, you can indicate it like this, and in the temperature entropy diagram, you can indicate like this. This is again, you can simply analyze this with the equations like this. The energy balance, you can read about this one. The same thing here, Q in, Q out plus this thing is equal, plus work in and work out is equal to enthalpy change in the system. Okay, the heat input, you can say, you can talk about the same positions or same denotions like 1, 2, 3, 4, and here you can for the 4 processes you can write these equations. W is equal to this much, W out is equal to this much. All these things you can talk about simply using the enthalpy, but here the pressure changes are taken into account. Thermal efficiency under cold air standard assumption, you can talk about this temperature using pressures with the K value, and you can usually we give the ratio of pressure, like earlier we talk about volume ratio, right? The compression stage, you have the volume final stage and initial stage. You can talk about the compression, the ratio of volumes as well as ratio of pressures, and we talk about this RP. These RP values are given in tables also if necessary. if you cannot find other properties, you can use this one to locate the other position in ideal gas turbine. Now, I don't think that I have to explain all these things. This is simple mathematics, you can see, because I talked about Cp and Cv values and measured in room temperature. So, enthalpy is, you can simply say, now here it is for a unit mass flow rate, but if the mass is incorporated, then you have to put m here, right? So, I am not going to explain all these things. I hope that you can understand this one. If not, please let me know. Now, as I told you, this is again, we were talking about the ideal case or the constant entropy process, but again here also the entropy changes and also temperature changes when you do things. Usually we assume that we can talk about this pressure lines in a same line rather than changing little pressures, or this ideal case is can be taken with the assumption that it is constant pressure, right? But in the real case it is not so. If you take that all those things into account, it will be a little complicated, but entropy change, of course, you will have to, if it says that entropy changes from here to there, then you have to incorporate that rather than the pressure changes, because the pressure ratio is also given, so that you can think about how these things are taken into account when you analyze a cycle or when you analyze a system of this gas power cycle or steam power cycle. Similarly, right? Now I will stop at that point. Combine cycles, we'll talk about all these things in another lesson, because combined cycle, of course, this is very important thing. When you talk about cogeneration and polygeneration also, we have to talk about lot of things in combined cycle. Combine in the sense, in the gas turbine, I told you these exhaust gases are once out from the turbine, it's in very high temperature. You can use that temperature, high temperature exhaust gas in a steam boiler or in a heat exchanger, where you can pass water and take superheated steam into turn another turbine, so that you have a combined efficiency. Now this is what you call this combined cycle, gas turbine, gas cycle and steam cycle combine using a heat exchanger, which we call heat recovery steam generator. Now this is what we have in all these thermal power plants, and in Lakvijaya power plant we have the combined cycle. So you can think about separately how this gas plant separately will be different efficiency. Steam very low efficiency, but once you combine it can go more than close to 60, right? But usually gas turbines are a little bit about 40 or 45, but in steam turbines you never go more than 35, I think, right? You can increase with very hard or with difficulties a very little, but combine, then it will have a more efficient system than the systems isolated as a steam and gas ones, right? So we'll talk about Otto and diesel cycles and combined cycles in another class, because it's very difficult for me to talk more. I hope you got something out of this one, and I will continue from here in another class very soon. But I will give you some assignment will be only from steam and gas cycles. Okay? Happy? Enough? Okay. Two more messages. Isentropic efficiency always deals with the ratio of work done between actual case and ideal case. Yes. Work or whatever it is the quality, as I said. So it is always the ideal and real case, right? Got the point? Because ideal case, it's the constant. In the real case, it changes. So it is the work out or work done or the changes of the stage in ideally and actually the quality changes because the entropy or this property change. Okay. Right, we will stop at that point. I'm so tired now. Talked for about 2 hours, nearly 2 hours. Uh, you can tell me after, or else I will arrange another class very soon to talk about Otto and Diesel also, because I think you as a help to the people who doesn't have thermodynamic background or this science background in their basic degree. So we'll talk about that also, then you can it may help you, right, rather than studying alone. So shall we stop at that point now? Any questions that you want to ask? I can, I mean, we can, because it's about a lot of people here, so I didn't want to ask you individually who you are and where you work. It's very difficult, right? So if you want to tell me anything about your work and how important this kind of subject matter in your work or in your career, please let me know. Rishanti, what is your position in, where are you working? Because I know her name as the representative, that is I'm talking to her, right? So don't think bad that I'm not talking to others. I can ask others also if anybody want to tell me something. Rishanti?
Yeah, ma'am. I'm
Yes.
working for a international NGO called V Effect.
What's it?
V Effect. It's a
The effect.
INGO. Yeah.
Okay. What are they doing?
So we work with like cooperatives.
Uh-huh.
Yeah. So our main work is like to do with food security.
Uh-huh. So what is the relevance of this degree program for you?
So this is because like I also work on like circular economy and sustainable
Ah, yeah.
development. Yeah,
Mm.
that's
So
right.
this may be a little bit difficult for you, right? Because we
Yeah,
are
like but the energy part is new, but the
yeah.
circular economy and
Ah,
the
yeah,
rest is
okay, of
yeah,
course.
yeah.
It's kind of a what is your background actually? Basic degree?
I have like masters in international study one, and
Uh-huh.
then I have another masters in political science and global affairs, and
Ah,
also
okay.
gender and peace building. So it's a three masters.
This energy part is maybe a bit difficult, but you can, I mean, talk to me at any time, or you can post questions if you want more things. But ebooks are there, thermodynamics, right? You can just refer them if you have difficulties. And others, can I talk to any other person? May I handpick? Okay, who is this? Well, somebody was chatting with me. I'll get one. Who is Maheshwaran? Are you still there?
Yes, ma'am, I'm here.
Okay. What is your background?
Uh, I did BSc Physics.
Okay.
Yeah. Uh, to my career, I think it's important part. Uh,
Where are you working?
I am a physics teacher also in Visiting Academy,
Ah, okay.
BRSC,
Okay.
particular center.
Okay. Okay.
Yeah.
So I hope in your basic degree you must have learned about this physics, right? Thermodynamics is
Yeah,
actually
yeah,
a
yeah.
kind of
I did.
physics.
I
Okay.
did. I did.
Okay, okay, good. Then there's another one who chat here, Shanaka Ratnayaka. Are you still there?
Yes, ma'am, I'm here.
Ah, okay. What is your background?
Actually, I also followed BS honors in physics.
Ah, okay.
Last year only I have passed out. So
Okay.
I thought to move into the industry. Therefore, I am following this course. I think this course is more important to me because I need to move to the industry with my physics.
Okay.
To move that one as a qualification, this is more beneficial for me.
Are you working at the moment?
I am working as a TL in the university,
Ah, okay. Where, in which university?
Eastern University.
Ah, right. Okay. Okay. Good.
Okay.
Okay. I mean, Eastern is Oluville? No, where? Eastern
No,
is Minko,
Baticola.
right? Batigal.
Baticola,
Right.
yes.
Okay. 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 Another one, Athukorala. Are you there?
Yes, madam. Good evening, madam.
Good evening.
Yes, madam. I'm working at Sri Lankan Air Force as a mechanical engineer.
Okay. So you must be knowing your
Yes, I am very aware with the thermodynamic
your background is
mechanical engineering. I
from,
have a Bachelor of Engineering degree.
yeah, where from?
Sorry,
Bachelor of Engineering degree from which university or which institute?
Engineering Council, United Kingdom.
Ah, okay. Okay. So you
And
must have
also
followed all these things, and
yeah.
it may not be very difficult, but you will have to anyway.
And also I followed the High National Diploma in Engineering.
Okay, good. Okay, so you all can, I mean, post questions in the discussion forum. I will put a forum link into the LMS tomorrow. These days, actually speaking, I'm in a very tight schedule because as you may know that we are the country actually, you can't say University of Peradeniya, but the engineering education in the country started in 1950, 1st of July 1950, right? So that university is the Peradeniya University. Engineering faculty is celebrating 75th birthday on this July 1st. So we are having certain programs in that. But in general, you can talk about engineering education started in the country in 1950 in the technical college actually from United Kingdom. The syllabuses or the programs, the university concept came from British people. And so that I'm just telling you the history so that you can think about how this universities developed their programs after that. So we can say it is University of Peradeniya, Faculty of Engineering, but when you talk about the country, it is the engineering start of engineering education, right? So other faculties came after that, and now we have 7 faculties, engineering faculties, where we teach the basic engineering. And this master's degree program, actually this energy master degree program is another invention, timely invention where you incorporate all these circular economy principles into it from Europe. All those countries are developed countries. We have lot of things to take from their system, and it may be very difficult for us to incorporate all these things or develop into a stage. We will not see in our lifetime, not I don't know you about you, but I will not see any development than this in my lifetime. But we'll hope for from the people like you, once you study all these things, use for the betterment of the country and betterment of the humankind. Okay, so we'll meet again in another lecture like this or another health session like this.
Ma'am, excuse me.
Yeah, sure.
This
Madam?
University of Peradeniya Faculty of Engineering, are they arranging any exhibition or something for
Yeah,
that one?
exhibition is there's an exhibition in September 24th to 23rd to
Okay.
27th, 1 week. But July
I
1st,
think that, Madam, I think there has a 1 year program, I suppose, huh? To
Sorry?
celebrate. There are several programs scheduled.
Yeah. We have
and
done so many programs from January to up to
Yeah.
now. July
Yeah.
1st, we are having another.
we donate as a batch 2.5 million to the para.
So we do a lot of things. Which batch from which?
Is long ago. It's a E86.
Oh, 86 is not long ago, right? Compared to me, I'm
So
E82.
I was involving to collect the money from the
Well, tell me. So you must be knowing me, right? Before.
That's what I was figuring out because I was attached to the drawing office and the thermodynamics
Okay.
office. Dr.
I know you.
Sorry, what's
Yeah,
your name?
My name is Pires, A.R.A. Pires.
Yeah, Pires,
Okay.
I know you. I think, I know you, madam, because, I'm 87, 88. I think, this
Yes.
Jayakot is my batch, this
All right,
minister.
right.
No,
Okay.
the Leelananda is my group mate.
Okay.
So
The
you are the
D-
people. You are the
Dean.
people who came as soon as
Yeah,
we pass out.
actually,
Yeah.
madam, when we in the
I was
final,
thinking you in the first year drawing, I suppose.
could
You are
be
in which batch, madam?
I'm a 82.
E82. Okay.
E-
Yeah,
Okay.
we may come across.
Okay.
82 mean you must be knowing, I think, this Ms. Hamza, this
Yes.
Dr. Patran, Dr.
Yeah,
Patrana's batch.
Dr. Patna is from the production, I suppose.
Yeah,
Anyway,
he's
ma'am,
production head anyway, I know that.
since you no, we were studying the production engineering under the Professor Anadunga.
Yeah.
At that time, Professor Anavira is dean.
Dean,
Anyway,
okay.
since you opened the subject for
No, it's good. It's good.
extra-
I'm
yeah,
so
it's
sorry
actually-
that we don't have time to talk to
Yeah, sure, no issue.
everybody.
I was in
So,
the final year students representative on the anniversary of the 50 years of the
okay.
university.
Okay.
Go ahead, madam.
Good. Thank you so much for telling all these things. We will get to know each other very soon, right?
Dr. Indirani is my batchmate. I think she's in mechanical.
Yeah. She is here with me in
Okay,
the
anyway,
department.
I'm here in Dubai. I'll be coming maybe next week, and I hope hopefully I'll be
To
visiting.
stay until 1st of July. You can come visit the faculty, right? 1st of July, we are having some celebrations.
Yeah,
Okay.
I'll be coming.
Yeah, sure. Then we'll meet you.
Okay.
Good that we had a little chat also. All the others also can have a little chat because I'm always open. But the thing is, I'm so little bit busy and I'm now old, 60 plus the age, so nearing the retirement stage also. But well, I can share my whatever the experience and knowledge with you. So please keep contacts, right? So let's meet again in the next lesson. Good night, everybody.
Good night, madam.
Good night, ma'am.
Okay.
Thank you,
Good night,
madam.
ma'am.
So much.